I'd like to review just a little bit about the projection operators today to get the start here. And we're talking about projection operators that are diagonal. That is, the two indices are equal on the labeling of global and local symmetry. And the setting that I mentioned in the last lecture is given 6 times. This is a typical example here. So I wanted to just make sure that you understood what happened in this sort of worksheet here that lets us sum and get the diagonal projectors. And then what I want to do is talk very carefully about the difference between the coset symmetry labeling and the basic idea of the split classes. That's really an important and I think quite beautiful concept that we'll be able to use in many different settings. Now the goal today is down here at the bottom, and what I'd like to show is some really neat things that happen with the levels, the level clusters for all of the possible things that octahedral symmetry could present. We've already mentioned that the C3 local symmetry and the C4 local symmetry are very obvious in the spectra of SF6. But I'd like to acquaint you with what we call monster clusters, and those are when you talk about local symmetry that's just C2. It's just bilateral. And that means you have a lot of levels that are fighting with each other. And what they do, particularly the triple crossings, they all meet at a triple point. The question is, are those coincidences accidents or not? That's the sort of the physics question, but it's a mathematical physics question, which we'll explore. But before we get there, we got to make sure that we really understand how the classes, the cosets, and all of that fit into the development of the projectors that are giving us our eigenvalues and eigensolutions, wave functions for these objects. So here is a little diagram for the calculation of one of the projectors that split. I'll put it on both screens here and we'll work back and forth. Just to quickly show you what we've got is all 6 projectors. This one is the E component with the 2 modulo 4 subgroup symmetry. Then comes the triple projector, the triple representation of the octahedral group getting broken up here, and so forth. So these are all worksheets that presumably for large groups like our icosahedral specimen, we would arrange these worksheets on some silicon. That is, we would program this procedure, and then you can do in a group of any size. But that's what we're facing here, is just a very simple sum, and this one right here is the very first one that starts off looking for the 0 mod 4 representation. That's all 1, 1, 1, 1 coefficients. These coefficients here of the C4 symmetry. This is a scalar representation, so everywhere you see +1, +1, +1 as a factor that goes with a coset, or in this case this actual subgroup, consisting of 180-degree rotation, 90-degree rotation, and -90-degree rotation. So this is 90 degrees squared, this is just 90 degrees, and this is 90 degrees cubed. If you just read off the powers, the P quantum number that goes with the exponential, complex exponential that describes a particular representation with a mode number modulo 4 and then a power integer there. So that, first of all, has to be set up because these are the projectors that are going to split the all-commuting projector that goes with, in this case, the E indicates, as you remember, I pull one finger out here and make an E. That's a doublet. That's two-dimensional irreducible representation. Then we have to do the two three-dimensional representations. No work at all is needed. These are already just giving you as much splitting as that idempotent is going to do. It's all by its lonely self. So having this set of cosets here, you have all 24 elements of the octahedral group. And the idea is perform this sum right here, multiplying a sum over characters, that's these numbers here, that go in these columns that are indicated by the green arrows for each of the members of a particular coset. So these are the leader elements for this coset, R1, R4, I1, and finally RY is being represented here. And the number that goes with this comes from this table right here. Depending on which of these 5 classes it falls into, I put a number there corresponding to that. For example, R1 right here, that's in this class right here, so a -1 goes in that place right there. Same with R4, it has a -1 attached to it, but I1, which is in this class, has a 0 attached to it. RY, which is in this class right here, has a 0 as well attached to it. So it's these numbers that are going to be multiplying all 4 of these right here, and in each of the cases, in each of these columns. In the first column here, I just go -1 times +1, -1 times +1, 0, 0, so that's -2. That's the number that is the coefficient of this, and that's being multiplied here by this factor here, dimension over order of the group. 1 over 100, 1 over 48 is multiplying that -2. And then I have 1 over 12 multiplying everything here. That's the result we're looking for, is the split projector written in terms of all 24 group operators. So that result is right down here. Very last column indicating one of the numbers, a -0.5, showing up there. Well, that's from this -2 for the element I5, and it is this number here times this number, that's a -1. This number here times that one, that's another -1, that's -2, and that's all you're going to get because these are 0. And so those two don't count. I just have a -2, and then that scales to give -1/2. And you see there are a lot of -1/2s in this expansion. That's the worksheet that's describing how to lay out a projector splitting for a big group like this octahedral group. Okay? So I just want to make sure that that's clear. And then there are lots of other cases that will come up that we can do this way, and it's fairly efficient. And it's error finding. Usually you make a mistake, you catch it, because a lot of things have to be equal. Maybe not quite as equal as these, that's the scalar representation. But the next one, it's 1, 1, -1. That's the numbers that are here, 1 and 1 for Rosie, and then -1 and -1 for the two 90-degree preparations. So that those set of, it's colored brown now, all of them show up in every one of the coset registers of this worksheet.
Professor Harter?
Yes.
What if we had chosen one of the other, say, inappropriate projectors, say 1 sub 4?
If you had chosen
Yeah.
This
and
guy right
yeah,
here.
the one right above it. Say, yeah, that one.
Yeah, this one, we're going to have a 1, a -1, and then -I, and then +I. And that's in the next block here, I think.
What happens?
This is the T1 with the
Okay, we
0,
switched.
but the next one, this one, you'll see that it's plus, minus, -I, +I. And you do it column-wise. So for example, this particular column shows up with a -2I. This is a complex representation.
Okay, well, I
We're
asked a
doing a
leading question and I asked it
Yeah.
poorly. If for the E projector we had chosen one of the inappropriate C4 projectors,
Yeah.
what would have happened with our table?
Same thing. You name the subgroup you want
Would
to
it be
do.
0? I mean, if we had chosen one of the C4 that didn't correlate with an E?
Oh,
That's the question.
I see. If you don't use the correlation, yeah, it'll cancel. It's orthogonal. Yeah,
All of it all end with
Yeah.
zeros down in the
Yeah,
bottom row.
that's right. Yeah.
Another check.
Mhm. Okay. This is the last representation, 222, the tensor representation, remember, of octahedral. It's using those 4 subgroups too. Now, one thing that's true about this is when you do the cases like this one, we have a 1-4 in this T2, just like we do in the T1. What you're able to do is not bother with 3-4. It is just going to be the complex conjugate. And so everywhere you see an I in this, and there are 4 of them right there, you change the sign. There's another 2 right there, another 2 right there. You just change the sign, and you've taken care of the partner that goes with 1-4, which is 3-4. Okay, so that saves some work right there. That's one of the advantages of using complex, is you can set up, and you only have to do half as much work on the most difficult part. Okay, now, this is one way to summarize everything that we had there in terms of just factoring it into the cosets of the local symmetry C4 that we've picked to split this projector. So this is just writing it out without doing the arithmetic. And that's actually quite useful. These numbers, very often, if you just realize what's going on, and each one of these things is a different side of that cube over there. There's 6 sides to that cube, given that each one of the sides has a C4 symmetry. The numbers here will give you the overall phase of each side for a particular local symmetry projector. And these are projecting you as a sum over the entire cube. So they're giving you global symmetry projection. And each one of them has the local symmetry projector. It's just sitting there doing nothing. These numbers right here are sufficient to carry us through that sort of calculation very often. Wait. So this is a case of 10 split projectors in terms of 6 coset sums. Each one of these projectors represents a sum over all of the symbols on a particular side of the magic cube over there. Now, if you pick a C3, then you're going to be dealing with an octahedron, you see, and you'll have 8 triples in a sum like this, you see, and then each one of the sides would represent. You can see who the side's a little more difficult with the cube there. You just look at the triangular corners, and you can spot who's going to be in the octahedral local symmetry of C3. So that is something to contemplate. But the next slide here is the one that we will be using today, and this is a high-powered set of projectors. This is the one that really reveals all of the fine structure that an octahedral wave function can give you. And so all 24 elements of the O group are written here. We twice that much if we were going to do the A. But this is a case where you have a orthogonal transformation. These are 10 split projectors in terms of 10 split class sums. And you have to identify which of these are actually subclasses. That's the thing that I need to clarify by going and looking at the cube more carefully. For example, these all 6 were in the same class as the octahedron, but in terms of this local symmetry, with this local symmetry being a reduction of the symmetry from the octahedral, it turns out that these 4 that I'm pointing to right now are in the same class, subclass, and then this one is, these are separate. And you can usually tell this by looking at the numbers. If they're different, then they're probably in a different subclass. So this is a generalization of character analysis that is associated with a particular subgroup's chain, a particular splitting. These 2 guys right here are in the same class. These 4 are in their subclass. That's something we need to clarify. Right now they're not even written quite in the order they would be if we had taken that into account. But this is the thing that I find to be really powerful, and that's what we're going to discuss right here. We're going to look at the level clusters in a little bit more detail than we have so far. And in particular, we're actually going to be giving the eigenvalues within a particular cluster. Now, we've just breezed over this very quickly before. Okay, so remember when we showed the projective picture of the splittings that we would expect from this guy right here, which would give us an A1, an E, and a T1. And then this guy would give you a T1 and a T2. This one right here. The one we're looking at right now is that first one there. And what I'm doing is I'm looking at the numbers that were in that particular sum that we had. So I want to make sure that you see that, because now it is written with the classes separated. There's the original class of 8 things. It breaks in half. Here it breaks in 2/3 and 1/3 for that class right there, and so forth. This one has this guy here and these 2 separate. This one has 4 of these, 1, 2, and 5, and 6, and then 3 and 4 are off on their own. And right now, just looking at them as parameters, if they were the parameters that determined the tunneling, this is the kind of splitting that we would get. This is the actual picture of the splitting. And then, if you want to go ahead and extend and see what these parameters or these parameters do, you can do that too. So basically what this is doing, this is the I3-4 split. If I were to take that, so I may have this backwards here. This is the 1 to 6 split right here. This right here is +1 and +1, so no, that's those 2 right there. And then this one is at -1. Okay, so these are 2 possibilities, and there really are only 2 parameters that this system can stand to have, aside from the one that tells you where the whole thing is. That makes 3 parameters for 3 levels, but as far as splittings goes, the difference is there are only 2 parameters needed. So you pick some 2 sets here, and you're going to get either this or you're going to get that. That's what's really quite magical about this way of breaking things down. Now let me move this ahead here so that it points to the splitting that we're doing. Basically, this whole table here is being subsummed in this table right here. So you'll see For example, minus a half under the E setting here, that's this one right here. You'll see a minus a half and a minus half for R1 and R2, and then R inverse 3 and 4. Then there's inverse 1 and 2 and regular 3 and 4. They both get a minus a half, but when you're talking about the T, it can distinguish them. There's plus and minus I over 2 for that particular one. That would be this guy right here. Okay, you see a minus, let me make sure I'm reading that correctly.
Yeah.
Minus 1/2, is that C? I think that, yeah, here we are. Minus I over 2, plus I over 2, okay, for T1. This is the one that's complex, okay? So there's R1 and R2, each with a minus I over 2. Then there's R3 and R4 with a plus I over 2, and then there's R1 and R2. There's minus 3 and 4 inverse also with that. So you see this class right here with the inverse for the 3 and 4 and the regular for 1 and 2 gets the minus a half I over 2. This guy right here where you have the regular 3, 4 and then the inverse of the 1 and 2 gets a plus I over 2. So this is just a compactification of our worksheet, basically, the result of the worksheet. Okay, and you can see, for example, that the 0, 4, let's see if that's right, 0, 4 here, it's a lot of zeros, okay? Here we have 8 elements, all 0, okay? And you see those right there to that point right there are 0, okay? So, either one of these is capable of producing this, but this is a way to really see how those group elements serve as parameters. Now we have to discuss the geometry of them. Why are these 4 in a separate class, subclass, after we've done this C4 projection? That's something that is very visible by looking at that cube, the magic cube there. So here's another example of this with T2, okay? It's things. Now realize what we are doing here. This is a orthogonal transformation matrix from subclasses, 10 of them, to projectors, 10 of them, okay? So that's powerful to have that. Okay, in other words, in principle, if I was going to try to get the splittings for all of them at once, well, there's a unique solution to that. You name me all my energies for each of these guys, and I put it in the inverse of this matrix, and I figure out what all 10 of my parameters are. So it's an ortho-complete eigen system. That's what we've got here. But the geometry of it is quite amazing. Now remember, if you reassemble, this is a check of that table. If I just simply replace these guys together, put the thing together, what I will get by doing that, and you have to remember that there's a coefficient outside here, but you recover the character. In this case, that cancels that cancels that. So 0 is the result for this, and that is the 0 that's in this original character table. And the same thing goes for all of these. The i's all cancel. I end up here with 1 plus 1 plus 1, and then divided by the 3 that is associated with this. Putting these back together again, I get 1 and minus 1, and so forth. Okay. So putting them back together again means 1 and 1 is 2. Here it makes it 3, and here it makes it 3. So just keep that in mind. Reassembling this thing is just a character table. So this whole thing with the little numbers is a generalized character table. Okay, so we're basically generalizing character theory. And remember I said that that's the only theory that most of the people that do this kind of work knows about. Well, they don't know about this. And I think they'd be happy to know about it because it is invariant. Okay, now let's compare
Dr.
the cosets and the projectors a little bit more closely.
Can you go back one slide?
This one.
So, yeah. So in the last column, so you have like I2, I1, I2, I5, I6, right?
Right.
I cannot see how that splits in I2, but why wouldn't you put like I3, I4, I5, and I6?
All together.
Yeah.
Well, let's answer that. That I need to go forward to answer that one.
He's prepared
Yeah.
for it.
Yeah, this is geometry of the cube that you're holding. Let's take a look at that. That's this, okay? Now, realize that the O subgroup operators are these powers of 90-degree operations that we've named here. So we're talking about the z-axis. The z-axis of the cube comes out of this face, okay? And the operations that correspond to rotating around that face, that is leaving that face in place, are these four elements, okay? And the question is that once you've done that, what's the situation with regard to your classes? That is, here is the C4 subclasses, and you asked about the very last one, which I will talk about last. Let me take the first one
Corners.
first, okay? Because the question you asked is applicable to it as well. So what I want you to notice is that this subgroup of the octahedral group cannot transform the subclass operation R1 and R2 into R1 and R2 inverse. Now, why is that? Let's see where R1 and R2 and then R3 and R4 inverse are sitting, okay? There's an R3 squared, that's R3 inverse. There's R1 at the other top corner of this face. And then down here is R4 tilde, that's R4 squared. And then there's R2. So R1 and R2 can easily be turned into each other by the elements of this subgroup C4. That is, each of the rotation, 90 degrees, 180, minus 90, each of those rotations is capable of turning, say, R1 into R3 inverse, just by turning it by 90 degrees, literally picking up the crank and putting it over here, right? Remember, that's a class transformation, fore and aft, that we're talking about, not just straight multiplication. Okay? So each of these, as a transformation, is capable of turning R1 into R3 inverse and R2. Okay? You see, that's R3 inverse and R2, and then R1 finally can be put into R4 inverse as well. So all three of those are in this subclass. Whereas before, the octahedral group could easily turn any of these into any of those, and that was considered an entire class. But this subclass is different because you're only allowed to use the elements in this subgroup.
It's sort of analogous to taking your chosen C4 faces and pulling them apart a little bit. You see that?
Thinking of breaking the symmetry.
Breaking this, yeah.
Yeah, making it so that only that face has symmetry. Yeah.
The other ones get rectangular, so to speak.
Let's go one step further here.
What about the opposite face? Is anti-symmetric?
This guy over here.
Is anti-symmetric?
Yeah. That guy over there, this guy, that's what you're looking at right there as a coset, right? But what we're doing right now is we're just asking this local symmetry, how powerful is it? What can it do to various operations? And what you'll notice is that R4, I'm looking back at this one right now, R4 and R3 is hiding way down at the bottom there, opposite this one on the diagonal. Okay, and then the R1 and R2 inverse also R1, but R1 inverse is over on this corner, and then there's an R4 on this corner, and there's an R2 inverse on that corner. So we're talking about this a set of operations that are transformed into each other by these subgroup operators, you see. So I can transform within there using that subgroup, or within there I can do it. Now, here's an easy one. Let's take row X, that's on this side, right? Row Y on this side, but I'm looking at the operations. Row X and row Y are transformations around the X-axis, which is coming out of here actually. X is on this side, but I'm talking about now a 90-degree rotation. I'm sorry, a 90 or 180, but let's just take a 180 rotation there that would, move the whole face. What we're talking about is what can RZ do to that face.
Row
Okay.
X is row Y, and row Y is row X if you apply R, right?
Yeah, so
Their own
the
class.
row X and row Y are transformable by RZ, right? In other words, the row Y is 180 around that axis, okay? And row X is 180 around this axis, and I can turn those two axes into each other using this poor little C4 subgroup. But I can't turn row Z into either one of those, right? Row Z stuck here, these turns don't do anything to it. It just sits there when you apply this subgroup to it.
Subclass.
So this is a subclass all by itself, right? Well, it's all by itself, just like the identity is always all by itself. Now we have actual individual elements, and here's some more. RZ and RZ inverse also immune to transformations by themselves. A self-symmetry, right? Doesn't change an operator. So these are lonely guys with respect to the C4 administration. It goes into power. It doesn't have as much power as the whole group, right? So it can't make transformations that we used to be able to make. So that's the idea. I1, I2. Now this is getting to your I1, I2, 5, and 6. Okay, where are they? Okay, there's I1, there's I2, there's I6, there's I5. They're all rotatable by our Z subgroup, our C4 Z-axis subgroup. They're all rotatable into each other, all those R's. And all of the I's, there's I6, I5, I1, and I2. So that's why I1, I2, 5, and 6, they're all grouped on the face here, and they're rotatable into each other by this lousy low-grade Z subgroup that we're using to get our splittings of both projector and classes. So that's really a key thing. And then I3 and I4, where are they? Well, they're right there perpendicular to this Z-axis. So 3 can go into 4 and 4 can go into 3. But that's just a couple of them. So there's a couple of operators that are in their own subclass. And that's the way it works. That's the way this reduction here really works. Is that making sense?
Dr. Harter, that I4 you say goes.
Here is I4 sticking up out of an axis right
It's
there.
in the waist.
Okay.
So it just goes to I3 goes to I4, or I4 goes to
Yeah,
I3?
by a fore and aft similarity transformation. Remember, that's a transformation that you hit it from the left and then you hit it from the right with the inverse, right? If you're actually doing it with symbols, right?
It's
But
analogous
here we're
to saying
just,
they can use
we're
each
just
other.
doing it to the operation. Like we think of a crank here, and that 4 crank goes over, becomes the 3 crank, and the 3 crank comes over and becomes the 4 crank.
Similarity.
90-degree rotation would do that.
That's basically diagonalizing that, whatever that thing is, like putting it in its.
It's
Like-
turning the group on itself.
Yeah, that's what I meant.
Yeah.
Because, okay,
Yeah.
like every time. So if I, let's say, well, it's not always because. Okay, just let me ask you a question. So every time, if I just apply a similarity transformation to one of these.
That comes from a subgroup.
That comes from a subgroup.
Right.
Am I diagonalizing the not really, right?
Yeah, no, this is just moving operators around. That's all we're doing here. But we're doing it in a structure, this structure, that has the same splitting, that is into 10 pieces, that the projectors do, and the projectors are trying to do diagonalization. So it's a couple of steps to being talking about diagonalization. Right now we're just talking about group multiplication and moving pieces of the group around, in this case operations of the group around.
Yeah, because that's one trick I know. Like sometimes if I want to ask myself, if I have like an operator or a matrix or something like that, I ask myself if it is really invariant under a transformation. I'll always
Mhm.
do like the dagger, like I will like sandwich it between like the dagger and the
Yes.
the dagger of the dagger, which is just the itself.
Right.
Any operator I have, and that always answers my question whether or not it's invariant under
Invariant.
that transformation.
And the other way to state invariance,
Uh-huh.
besides saying that the transformation inverse leaves the operator alone, is to take that inverse and put it on the other side,
Well,
and it'll be on the right side.
Yeah.
On one side of the equation, it'll be on the left side. So that's commutivity.
well, that's the same.
That's
as
the
showing-
idea. The invariant thing has to commute with that particular operator if it's going to be invariant.
Isn't that the same as showing like the left coset and the right coset are the
We're-
same?
We're trying to avoid doing the right cosets, which will be different.
Oh,
They'll be
This is
permuted.
not a normal
They'll be
subgroup
permuted, but they'll be-
necessarily. Yeah, right? This one definitely is not a normal subgroup of O. Then you can go both sides and you have what's called a normal sub. A better name for normal subgroup is an invariant subgroup, right? An example of an invariant subgroup for this whole group is a 180-degree rotation around Y, 180-degree rotation around Z, that's rho Z, and rho X. Okay? That's our old friend D2, right? So the D2 subgroup of this octahedral group is invariant to all of the elements. So when you make a coset out of it, it's going to be left or right, doesn't matter. And it won't be necessarily very powerful,
That's nice.
for diagonalization, although it's not completely powerless. There is stuff you can do with D2, okay? But the C4 one really stands out because it's a lot easier, I think, than looking at the C3. C3's on the corners. You really need an octahedral, guy to look at it easily.
Yeah.
It's just slightly more difficult, hanging on the point here than it is to have a face. Okay. But you can see what the face is going to look like. They're the three things that go with it. Those are cosets of our friend 1, R1, and R1 inverse, which is hiding on the other side. But there's the R inverse, and there's the R1 that would be sitting just around the corner there. Okay. Okay. So, what I would like to do, I think, if this makes sense, is go ahead and use some of it. And remember, the main thing we're going to use is the fact that the parameters that go with these groups have broken up now into 10 separate sets, class splits, is what we are calling it here. Okay? So, let's go ahead and continue this level cluster business and point out, I want to point out in this gigantic spectrum, you got to realize this comes from angular momentum 88 here. The 88th bump on this pattern here has all this stuff, and we're just looking at this side of that spectrum that I've got circled here that has these clusters that come in fours. These are levels that are coming in fours. A1, T1E, T2, T1, A, E, T2, A2. These are the ones that come from the columns of the correlation table. A1, E, T1. Okay, to start right here if I want to, or here, or even down here, even a little bit here, because you're getting close to the waterfall where you go into another regime, but you see that there are here, 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 and here, all the ones that whose angular momentum is divisible by 4. Okay, not that one, but that one is divisible by 4. Not that one, but that one is divisible by 4. 0 mod 4 is the key number here for this local symmetry, giving us an induced representation consisting of 6 dimensions. A scalar 1 plus a doublet 2 plus a triplet T1. Okay, those are what are hiding in this box right here. Now the degeneracy doesn't show. That's global degeneracy, and we're floating freely in the outside world, so we have complete total symmetry of R3 or O3 there. So no splitting of that, but you do see splitting between the individual representation, but not much. This one's only splitting by 0.7 hertz. So this is less than 1 cycle per second in tunneling back and forth in that cluster. This one's got 4 hertz. This one's got 27 hertz. Okay, we're going up in the tunneling rate as we climb out of some kind of local valley. Down here you're talking about once every 50,000 years. So that's the 0 mod 4 clusters. Next door to it, 1 mod 4. Next door to that is 2 mod 4. 2 mod 4 to this, this, and this. These are the even clusters that aren't divisible by 4, by C4. Okay? They have a very different character to them. They're made of things that have 2's hanging off of them, T2 and A2. They both use E though, because it's more a threefold object. So that gives you a feel. What I want to do is get a feeling for, first of all, that this correlation table tells you which of these species you have in there, but now we're going to actually work out their splittings. What they aren't totally together. They have a little bit of air between them, so to speak, frequency between them. Now we're getting into kilohertz down here. And then we're getting into megahertz as we approach the waterfall. The separatrix is what we call it. So this is one side of the story. Then we have the other side of the story, which involves C3. So basically what we're talking about on this side of the story is a molecule that is only rotating on its fourfold axis. That is a SF6 molecule that is just doing one of 6 different things, either doing this, or this, or this, or this. Okay? Each time I hold up one of these axes, a fourfold axis, I can go this way or I can go that way. So together I have 3 axes times 2, or 6 states, corresponding to the angular momentum being localized here, 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 or here. So I've got 6 things that I'm going to break up into symmetry multiplets that represent global symmetry and living locally, having to be confined locally. Does that make sense? Is there, I mean, there's a lot more to say about this, particularly the spacings, but just as far as the who gets to live in what house here, that is completely determined by this correlation table here. And later on, a C3 correlation table is going to take care of the other side. But let's just get one thing at a time. This is the most popular clustering, C4. Reason for that has to do with the tensor Hamiltonian.
Dr. Harter, so C3 will take care if the angular momentum is in the separatrix?
Like this. Separatrix, another story entirely, and we'll get to that at the end. That's where you get the really screwy stuff, the monster clusters. Here we don't get anything there. It's just one or two levels in there and nothing going on. It doesn't want to live there. It's poison. Yeah, we'll see why that is. Yeah. Okay, so here's the deal. I just look at this, let these guys do the tunneling. I'm more familiar with what those operations do, so I'm just going to write it down straight away. This thing is giving us, if I'm just looking at the I1 clusters, 1, 2, 5, 6, remember those are the four that can make a tunnel. I got a +4 for this guy. I've got 0 for this guy. That's a T1. That's, you know, this whole representation is 0. And then this guy right here is -2 times that tunneling parameter. So if all the other tunneling parameters were 0, this would be my answer. And the idea is that either they are or they give the same result. That's the other thing that's quite amazing about this. This tunneling parameter here, x and y, either one of those gives me a very similar result. This one kind of weird. Okay, that's a whole different kind of tunneling built all the way over, turn all the way over, not just turn by 90 degrees. Okay, but this is a legitimate tunneling. Okay, I2, the one we 3, 4. Remember, that's a subclass along with 1, 2, 5, 6. Okay, so that is definitely. Should have closed that off. It's Rachel from Card Services. She's probably been called by her. Everybody in the United States has been called at least once by the nefarious Rachel. Anyway, there's the other possibility of tunneling. If you're going to go, all the way over, if you can do that, and that's a big step. So these tunneling parameters are really small. But if they weren't, if there was something in the surface that lets you go over, and there wasn't anything that lets you go next door, that would be your spectrum. But this is what we see. So the other tunneling is verboten. But then there's the next step here. Okay, 1 mod 4. It's just T2 and T1, and they're split by a single parameter, I1. Same parameter as this one. Okay, this wouldn't help it at all. That wouldn't do any splitting at all. Then there comes this guy, same thing except it's upside down. So this is telling us something about the ordering, at least the relative ordering. We don't know the signs of these tunnelings yet, so we can't state that we are being smart about the ordering there. And then that's the other way to do it, and it's very analogous to this one. And you see, this one makes a degeneracy of E and A. It makes a triple degeneracy if it happens. And we had seen that before. If you just go back 4 or 5 slides, you see that one. Then there's another T2, T1 situation that's virtually identical to this. And it claims that the ordering, whatever it is, would be the same for this and this. That's key, okay? So this is, you see, this is a very different way of doing this sort of group theory, in a sense of getting these 10 splitters, and we're going to have a different number for C3, but that is what we're after. Now, let's take a quick look at C3 just to see it, because it doesn't have as many. And we'll see why that is at the very end here, I think. But right now, the question is your angular momentum divisible by 3? We start off here, it is not, but 87 is divisible by 3. So is 84 and 81. 9 times 9, obviously divisible twice by 3. But every third one is one of these pretty big clusters, 0 mod 3. That means divisible by 3 with no remainder. A1, A2, E is not there, T1 and T2. So we get every representation of octahedron except for the E. And then in between that are 2 that really are quite the same. T1, E, T2. T1, E, T2. In that order, which your tunneling will show us is the case. Okay. Same sort of thing happening here with the T1s and T2s. T1, T2, T1, T2. The ordering of this genetic code, or whatever you want to call it, is sacrosanct. It's the same on both sides. So that's what's going on when the molecule gets rotating around. One of the 8 possibilities, okay, 8 surfaces of an octahedron, which would be rotating around the center of the plane of the octahedron, and there are 8 of those faces. That's why it's called an octahedron. And so you have a dimension of each of these clusters as being 1 plus 1 plus 3 plus 3. 6 plus 2 is 8. Or 2 plus 3 plus 3. So each of these are 8 dimensions, just like each of these are 6 dimensions of the counting number of axes available to do rotation. Okay, is this, filling out the things? Now, let's really quickly go through and see what the ordering and spacing is. It's really quite beautiful.
Dr. Harter?
This one is equally spaced. There's 2 units between each of those guys there. That's kind of neat, right? And then this one also, nice balanced, equally spaced. So on the threefold axis, things are balanced. They're not this crazy thing where you have the A twice as far down and each half is way up, right? These guys are nicely balanced. Okay? But they're not, not the only way. This one has 3 different ways to split off. I can put A1 and A2 together and T1, T2 with this kind of tunneling. That's 180 degree. Again, highly improbable. And then these eyes, the ones that go with 2, 4, and 5, okay, number 2 of our possible thing. That's the way it breaks up when you do C3. So you got to go through the calculation we did for C4 in order to get this particular table here. And it even has some funny looking numbers that have square root signs in them to make it thing. Now, get used to that if you're going to be doing a icosahedron. Every single one of the clusters is some crazy irrational thing made out of golden ratios and stuff like that. Here, they're rational. So these clusters, when they get excited, will be periodic. These C5s are quasi-periodic. They essentially never return. These return every 4 or 5 cycles. I should say every 2 or 3 cycles is what that does. Okay, so we're going to try to rush a little bit now on some more secretarial work, but I do want to point out that this clustering correlation, okay, correlation for the O group is not complete symmetry analysis. We really should be doing all of the OH operators just to check out what the wave functions for the angular momentum rotational wave function would look like. Would it be even parity or would it be odd parity? This does not deal with that, but this does. So this is the OH symmetry the global OH, which is 48 symmetry operations that include half of them operations that would break this particular toy molecule. Okay, if I want to do an inversion of this thing, I gotta rip it out and put it over here and so forth. In other words, if this is a human being, this would be murder. Okay, the other half of the octahedral group would be murder. Right, instead of just turning, I'm dead. Reassembled backwards, but dead. These waves, they love to reflect, so inversion is no problem for a quantum wave. So you really have to tag it, and that's what we do. These are all gerade, that means even in German. These, and oh, I forgot to fix that. I always had a G where it shouldn't be. That should be a U. Fix that thing finally. But in any case, what you're seeing here is A1G, EG. Remember, they're both, this cluster is both even for the top and the bottom level. This is the top level, this is the bottom, that was the ground state. And then the T1 is a U. This one is odd. That was a P-like wave. This was a D-like wave, very even angular momentum. 2 is its heritage, and so is the A1 by definition, scalar, the S wave. Okay? So the old atomic way of looking at things is hiding in each one of these clusters. The next one, B prime, that we go with, that is there, and so forth. Now this is a picture that is reminiscent of diagrams that you see for solid state physics in the K-space. What you're seeing here is the center of a cube face, which you recognize having these elements of C4V. Before, we just worked with C4. 1, 90 degrees Z rotation. Didn't have any reflection. Didn't have this reflection. Had 180 degrees Z rotation. No, none of that reflection either. And then the 90 with a minus sign, or a 270 degree rotation. 270 coming all the way over to there. So we just worked with those 4 to do the stuff that we have showed today. Now add all that and you get this extra information about parity. Okay. So this is a particular local symmetry point. It's like one of those points on the Brillouin zone diagrams. The gamma point is usually a center, it's kind of closely related to that, but not quite. And then there would be sort of an edge local symmetry, and then there's a corner local symmetry. This with respect to the fourfold local symmetry. So these are the main local symmetries, and of course there are multiple versions of it. There's 6 versions of this. There are 8 versions of this. And what we're getting to pretty soon here is 12 versions of this. The local C2 is the monster cluster, which we don't see in the spectrum that we've seen so far, but there are ways a molecule could do that. So here is C3V. Now we're looking at this cluster that we've already seen. Well, this is what it's going to look like if you go ahead and do the full OH symmetry of it. Again, this will be a nice symmetric thing. The T2, it's angular momentum 2, so it's likely to be symmetric. Well, it says it absolutely will be. And here's my darn G that I didn't get rid of. That has to be a U, okay? Doesn't affect this thing, but that's right. That's a U. And so is this. T1 is always odd. That's a dipole right there. Okay, so it's got 2 evens and 2 odds in its clustering. Similarly with the other possibilities, now that we're using C3V as our thing, instead of just little abelian C3, C3V gives you, well, it gives you a splitting of idempotency. that has all real numbers. If you don't like complex numbers, this is what makes it easier. Okay, now C2 has got some problems when it comes time to bring it to the C2V local symmetry, the one that has eyes in it. This guy right here, and I put a little eye up there. And I mean that this kind of eye, the ones that we had 180 degree edge rotations. This one is involving 180 degree Z rotations. It has an ambiguity. There are two ways to make the cluster state there. So that's important. This thing splits into two A primes, and they need to be diagonalized, as it were. And there's another one down here. Okay. So what we're going to have to do is we're going to have to get not just a projection operator for this job. We're going to need a nilpotent projector, not just item-potent projector. We need a nilpotent projector to make a whole matrix, to diagonalize. A 2x2 matrix is going to have to be diagonalized to set this kind of clustering. And if we don't do the parity thing with our C2, we've got a whole bunch of 2's to worry about there. The C2 with the I, which is actually the one that we'll be dealing with, we're going to have either 2 of the T2s on the cluster, or we're going to have 2 of the T1s, depending on whether it's even or odd at the local geometry. So these are things that are going to come up at the end of this discussion. Now there's a whole bunch of bookkeeping I need to go through a little bit of, but I'm going to sort of rush it since it's something that's pretty well written up in these, well, this article here, and there are pages before this is actually linked. I'm going to finish these links just so that they're always available on every page.
It's on page
just to
2.
make it so you can jump to see more about this. But this is kind of looking at the local symmetry that is associated with this. I want to catch up on this projector as well to get to this picture here, just to point out a couple of things. And since I'm going over the edge of that board, I'm going to move over and stand in front of that one to point out that if we really have octahedral global symmetry and octahedral local symmetry, that's kind of almost cheating, but it's definitely a possibility. And if you take it down to C4 local, well, it involves a diagonal matrix. It involves 1, 2, 3, 4, 5, 6, 7, 10 idempotents. Okay, so this is a situation that we've mostly been thinking about here. And then the other possibility that also has 10 is C3. Okay, so basically what we get to do then is just read off diagonal idempotent projectors. But when you go to C2, look out. Right here, okay, it requires off-diagonal projectors, you see. So we're holding off until this point to say, oh my gosh, if I really want to finish this problem, I've got to bring in all the rest of the projectors that I normally would ignore, the ones that are off-diagonal. So that's 24 projectors for O. We've been getting off easy here by only have to dealing with 10. But as soon as I go for C2, I'm going to at least need some off-diagonal guys to take care of that one and that one in general. Then as you lower yourself to even lower symmetries like C1, well, then you're going to have to deal with all 24 of the parameters that come up. If the Hamiltonian for some reason is not Hermitian, if it's Hermitian it's less than that, we're not counting that. But this is the raw C1 local symmetry. If we have that, you've got clusters that have 24 levels in them. Each one of the levels degenerate by double for E, triple for T, and triple for T2. T1 and T2 have stacked up 3 identical matrices because I have not touched the octahedral global symmetry. As soon as I touch it, then those all split as well. Remember this sum of the dimensions squared is the order of the group, right? That's what you're looking at basically with this complete breakdown of local symmetry. There's no symmetry at all. Then I've got 24 copies of this thing just from the octahedral group. Now OH, then it's 48 squared that you're talking about. So you see how this can blossom into really huge problems. And as you go to various D4, D3, and even D2 symmetries, you get different numbers of parameters that show up in your calculations. Okay, these numbers that lie below there are just telling the sort of dimensions that you would have to work with when you were all done with the eigenvalue problems. So let's just review really quickly here. These are the fundamental definitions that set us up to work with projectors that are not diagonal. Okay? The basic idea is that these things are placeholders for each representation component. And you get them by doing an MMGNN. So that's a bit of work right there. If you were just to go ahead and put 24 things here and 24 things here on a single element, when you got all done, you get one number. That's a pretty inefficient way to do this. But of course, if you have a computer to do it, no problem. If the group's not a monster group. If the group is a monster group, then you got a problem again. So the G as a sum of projection operators and the placeholder is really a key idea. And then that expansion's inverse, and these are, actually that is a little bit misleading. I thought I had put a different link there, so that's another link I've got to fix so that you can go back and look at where all of this was put together. And the problem is we need to derive both these quantities, and they really are related to each other, so getting one gives the other. And very often the easiest thing is to look this one up and get that one. That's really easy. I just look this one up and get that one. I'm done. But if you're starting with a new group that no one's ever touched, that's what this course is about. You need to think about ways to handle this. And the basic idea is we know that if I do this, I've got a question mark right here, and that question mark would be this coefficient. So I'm thinking about this equation right here. So the first is to use the diagonal projectors to get something proportional to one of the non-diagonal ones. Okay, so we got touched on this already, and the operator transformations are also available to us to get the D numbers, components. So projector normalization, of course, is behind a lot of this. So thinking in terms of ket vectors, the actual wave functions, that's kind of the easy way into this thing. But also, if things are nice, if you are working, say, with a diagonal projector that's obtained by a splitting, like the C4 projectors, and they, of course, go on either side, because this is an all-commuting idempotent from the class algebra, then this is the thing you're trying to split, first into diagonal, but now we want something that's off-diagonal. So the idea is to reduce it to a smaller thing to calculate. So here I just go through and review what we did with C3V. So this is quite a few slides that we've looked at before, so I'm sort of going through this really quickly. Basically the idea is I do this, I get something that's proportional to, if I do this right here, I get something that's proportional to I'm just using the subgroup C2 to split the projector, and then get an anti-symmetric and symmetric thing for an element that doesn't commute with that. So I have to actually multiply it out and get this question mark number right here. So using the definitions that I was pointing at, I come up with something that has the answer up to, this thing is up to a factor, and the problem is, what's that factor? What is the overall factor? So here's my answer. I simply say, if I multiply this thing together to get this, I've got this thing squared, so I just have to match that with what I got from the splitting of the diagonal projector that came from the class splitting. And taking the square root of that, plus or minus, I get something that is indeed the correct answer. But is it plus or minus? You see, this is plus or minus. We need to get that. So the way around that is to do some kind of transformation where it actually is given to us. We have to actually figure out whether that is plus or minus. So we go ahead and do a transformation of these two. That's R coming from the left, so it's going to be the left index that gets summed over, and that's you can work those all out either way and produce finally a minus the square root of 3 over 2 for one of them and the opposite for the other for the particular element. So as I pointed out when we talked about this in C3V, this is the world's most complicated, perhaps, derivation of the sine and the cosine of 120 degrees. That, you know, is something is rather humbling when you consider that the top-down approach to all of these groups a lot faster. You know the sine and cosine, right? You're done, you see. And so we could have done that with the octahedral group. The problem is you miss all of the hidden structure due to the subgroup splittings. So this is one that I'm showing here. This is a coset factor T1 sum, and you can see just using the diagonal projectors, each one of these matches this formula, okay? And this is a formula, of course, for a non-diagonal in general, but it also works for the diagonal cases. So this is just going through the left cosets of C4 and putting in numbers on the diagonal that we already know, okay? And the question is, how do you get these other numbers? And one of the things I want you to notice about the representations that I have in tables in this textbook and also in these lectures is they are broken up according to cosets. In this case, it's a coset of rho x, rho y, and rho z. That's our new nomenclature for the old notation, R1 squared, R2 squared, that's y, and R3 squared, that's z, 3 for z, okay? So this is the group D2 right there, and then if you take with it the operations I3 and I4 along with 90-degree rotations R and big R tilde around z-axis, you have an entire subgroup D4 broken up into coset of D2 and D2. So all of the tables of representations really should be worked out and then plotted as cosets. Here is a coset of D2, here's a second, if you call a subgroup a coset. This would be the second one, third one, fourth one, fifth one, sixth one, you see. Or this is the subgroup D4, here's its first coset, and here's its second, okay? So all of the matrices should be tabulated that way, and then it's really easy. You find out there are all kinds of things that have simple relations, particularly the things that are zero stay zero, and then you get very similar results on the off-diagonal part as well. So the rest of this I'm just going to rush through because basically what it's going to be doing is saying, I don't want to do 24 times 24 things. I'm going to just do it with this subgroup, in this case C4. That's a lot easier. Find a nilpotent proportional to it. That will be the nilpotent we're looking for. So I go ahead and I multiply that out, you see, and then see what it comes out to be, sum up some things. And you'll discover they're the cosets, like two of them give you 0. Turns out all of these here are 0, but these guys are the ones that survive. And right now we're looking at the most off-diagonal element in this thing. So that we get pretty easily, except up to a factor, you see. And you have to do one transformation in order to get that factor. That's the catch to all of these things. Okay, so that's a typical table that's in the PSDS book. It's literally copied from it, stuck here with a labeling. And the basis that we're doing, you see, we're doing a subgroup chain. T1E14, T1E34, that's minus 1, 4. And then T1A2, 0 mod 4. So that's the kind of representation that we're working with in all of the stuff that we've shown eigenvalue and idempotent relations to. Okay, so this thing then continues to produce a number that we can trust. Actually, I left a couple of things off there. I think get busy. Anyway, here is a C4 subgroup chain, complete set of representations done with a D4 intermediate, which makes things a little more organized. But it's still an x plus iy, x minus iy, z basis for the vector. Then it's this weird kind of combination, similar combination for the tensor polynomials. And this one you recognize, x squared plus y squared minus 2z squared. That's one of the D waves. The other D wave that gets to use is that one. That takes care of E. And these two together make up the entire D wave of 5, count them, 1, 2, 3, 4, 5 angular momentum states for angular momentum 2. Okay, now here's another subgroup, D4, D2. I'm very partial to this one because most of the numbers are 0, or else 1 and minus 1. So there's a T1, there's a T2, put the whole thing on one piece of paper, and there's E. And notice that it's very unfaithful. That is, all of the elements of D2 are unit matrices. All the elements of the first coset are the same. These are all the same. These are all the same. These are all the same. And these are all the same. So it's that representation really easy to tabulate and use. Recommended because it's mostly zeros, so your sums are very limited for making wave functions out of this one. Really makes a difference what subgroup chain you pick in this business. And most textbooks don't make that point at all. If you want to have easy things. Now this chain is really remarkable for something that we haven't done yet. And this is the most powerful that I know of, most powerful mathematical physics I know of, uses what are called young tableaus.
Yeah.
So this I want to point out real quick right now, just to get you ready for it, because that's what we have to do. This is a subgroup chain that it really knows where it is at, so to speak. This is a subgroup chain that starts with S1. That's a permutation. It isn't a permutation. You just have one particle. But if you have two particles, it's S2, substitution 2, substitution 3, 6 factorial. That's D3 right there. That's C2 right there that we've been working with, right? This is our O. Our O is a isomorphic to permutation 4. So is TD isomorphic to O, isomorphic to this. So the bases that you see listed here, instead of showing the subgroup chains that we're used to, just put them down in boxes that indicate how they break up. If I lose the 4, I get the double dimension E representation of S3. If I lop the 4 off that, this one becomes the antisymmetric representation. Whereas over here, if I lop off the 4, I get the E, all right, but then I get a symmetric representation of the S3. And then this guy on the, I should go to the next page here, on this one, let's really quickly go there. This is the E representation here, and it's indicated by numbers in a box-like thing. This is, if you have a 4th rank tensor like the Ricci tensor, or I should say the curvature tensor, that's a symmetry. That's how you know. It's this weird kind of combination of antisymmetry and symmetry. So this is something to come. We have to, after the break, we will tackle what this is. Because you have a very funny hook length formulas for these matrices. The generators of this group can be tackled fairly, I should say, amazingly powerful. I also want to point out, if you pick different subgroup chains, okay, for example, that subgroup chain that has all the zeros, the D4, the D4, D2, and this is one that has some inversions and reflections in it, just to make it a little more interesting. That one has a lot of zeros in it, whereas the one that has to do with the C3, okay, I should say the D3, it's very often square roots of 3s and things like that, so it's not 1s and 0s. Okay, so here's just comparing two representations from different subgroup chains. For example, this one would be compared to this one. This one's completely diagonal, this one's definitely not. Okay, that thing's very at home with the XR1 squared, because it's D2, the final link. That's this final link right here making that one diagonal, okay? But this other one is S2 diagonal, okay? I4, that's diagonal, okay? I4 for this one is quasi-diagonal, it's got 2 by 2 in there. This IR1, okay, is got zeros and ones, it's not diagonal. The IR1 for this one is quasi-diagonal. So just to get you a feeling for how different are choosing subgroups. Very different. These are all T1U representations. But the subgroup chains are different.
What does quasi-diagonal mean?
What does what?
Quasi-diagonal mean?
2 by 2 and a 1 by 1.
I mean, but you, like, I want to visualize.
It means you've got a sub-representation. You're in a subgroup that's a part of the chain that's lower, right? So you got an E type representation here. You recognize that one, right? 120 minus.
We just did that one.
Yeah. But the idea, of course, is that this is 48 elements can go here, right? It's OH we're talking about. Okay. And these are just some samples. And it's T1U, so I can just get out XYZ coordinates and make it, right? This is the top-down derivation of those components if you wanted to follow it. Okay, we've got to rush here or we'll miss out on the things. This is one thing that as I say, you can, with these off-diagonal representations, now that you've got the full projector set, you can then produce the actual Hamiltonian matrix with all the parameters if you want them. I'm only doing the I parameters here. Okay? And most of the time, you're going to get a contribution off diagonal. In fact, you always will, if you use the full parameter set of any of the class of parameters. Okay? And the idea would be that if you make I3-4 just a single parameter, that is, you make a parameter I3 and I4 equal, and at the same time, make I1, 2, 5, and 6, remember that's the other subclass, right? If you make them all equal, all right, then you have the situation that we had in those tables where we were just writing off the eigenvalues. I1 equal to I2 equal to I5 equal to I6 kills that one. Kills that one. Kills that one. Kills that one. Only thing left, diagonal. Okay? With those particular values. So this is the E, T1, and T2 thing that we would get if we just used the I parameters. And you can see that if I don't make those local conditions, then we're going to get, after we diagonalize what's left, we're going to get mixtures of these local symmetries. Whereas all of the things that we did, we set it up so we came in with a local symmetry and demanded it. Now by demanding it, we're just simply saying all the things in a subclass have to be equal. And once they are, then you'll just get whatever the diagonal gives you. Okay, so I think that is a lesson that should be pointed out. Once again, this table makes that point. But what I want to look at is the C2. There's no C2 symmetry clusters between these. You've got C4 on one side, C3 on the other side. This molecule doesn't want to rotate on what is its saddle point. No C2 symmetry clusters between C4 and C3 bands because the C2 axes, the I axes, these guys, they're saddle points. You can't store any phase space there. You end up with either this, or if you're in the value, you end up with the C3s that we showed, but this is a really healthy example for J equals 30 of the spectrum that we expect in the highlands of this rotational energy surface.
Dr. Harter?
Yeah.
What molecule is this one?
Well, this is
What family of molecules?
it is mirroring a molecule that looks very much like it. But these are energy versus angular momentum direction. So this is in momentum space, angular momentum space, plotted radially. And that's our rotational energy surface, which I've talked a little bit about, but maybe not enough. But this is the thing where we put the angular momentum cones on there to find where the quantizations are. Remember that?
Yeah.
So that's what we're dealing with here.
Well, but this one is, compared like to the example you show us, this one is a monster. This one right here.
Well,
I mean, you show us like the simple one, like with the...
that was for the diatomic or the linear or the asymmetric top. That was for actually for water.
Yeah.
But if you straighten water up, that's what it was for, right? You made this type of thing, right?
Yep.
That's what that one was. Nice and symmetric, right? Simplest rotational energy surface. The next simplest is the bar of soap, right? The anti-symmetric, asymmetric one. But this one is the one that's got what we're going to see in just a minute here. If you just add one higher harmonic. So what I'm going to do here is I'm going to, in addition to the fourth rank tensor, I'm going to put a sixth rank on. So this is what happens. And you're going to get some monster clusters from this thing. So we're going to be seeing C2 clusters. That's what, this is when local C2 symmetry dominates. Now this is what's in the textbook, PSDS, and so I'll link to that page. This is what we were working with. Now we're going to add some of this. So we're going to have a linear combination over cosine and sine of T4 and T6. So this is a parameter, just to change the Hamiltonian. From this to this, which is all C4 clusters. That's all you get is C4 clusters. You don't get any of the stuff that's in the valley. The valley's gone. But then whatever volcanic activity is causing the valley to go flat becomes a mountain, right? In South America, you have lots of volcanoes that show up in a cornfield, right? Well, that's what's happening here, except that I'm here, 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 and here, right? And finally, it gets really crazy. It gets this big. Here's one that has nothing but C3 clusters. This one is nothing but C4 clusters. and then this one kind of has a little of both, okay? But this one has C2 clusters. See, there are 12 of those canyons. In addition to other stuff, the same thing, right, for that one, okay? So these are the formulas for the fourth rank, which we kind of looked at already. This is the polynomial that goes with a sixth rank that has scalar OH symmetry, that is cubic. And this is what we have to look at in closely. Now this is what always bugged me, was there weird things were going on there. I couldn't see what was happening. That's what we're going to do, look at right now. Here they are in color. Starting right here is the spectrum that we've already looked at. 2, maybe 3 C3 clusters. A2, T2, T1, A1, and then a T1E, T2. And then we're going to try real hard to make another one, but it's kind of sloppy. And then we're over the separatrix now of this thing. We're out of the valley and onto the mountains, and it's all mountainous clusters, C4 clusters from here on up, described by this table, okay? But then, as I add this stuff, actually it's something between this and this, that I add a little bit of it, all of the clusters get together to make C4 clusters. There's nothing but C4 clusters. A little bit of noise there, it's really sensitive. You just change this a little bit, boy, it jumps to something else. And then, here are your C2 clusters right here. That's when local C2 symmetry has a dominant region like this. That's what we're talking about.
Dr.
right
Harter,
there.
how did you generate these guys? That was when you were in Los Alamos.
No, this is, for this paper, this is fairly recent. You know, we did this in 2014, and we're going to do it better now. Promise?
Yeah, I can make that.
Yeah, we'll have,
But
this
give
was,
credit, Justin Mitchell, right?
Justin Mitchell worked out a program that did a pretty good job. And the idea, of course, is to tell by color which representations you're seeing. Okay? Dark blue, T1, light blue, T2, E is green, A2 is orange, there's an orange A2, and there's only one of them in this thing. There's 2 of them, I'm sorry, there's one A2, no A1, then there's an A1 again, and there's an A1 hiding in there. If you look closely, that's what we got to talk about, what's going on there.
So there, I'm not seeing orange I will call it
Right
geodesics.
Right there.
Oh, they are there. Oh, I cannot
Yeah.
see them.
Well, that's the thing we have to improve. We have to make it so these colors mix chromatically.
Or be able to separate them out,
Yeah,
or
be able to
enhance one, or...
Yeah, we'll have power with the graphics to do
And
that.
I have a question. Do you have a plot
And look
in
at this one over
in
here.
the
This is
momentum
all
energy
C3.
space for that molecule?
Pardon?
Do you have a plot for that molecule?
Yes, we do. It's black and white. We'll talk about that later. This has got
You can add
enough.
to it.
Yeah, there's enough in this one to keep us busy, certainly for the next 5
Same
minutes, which is all we
technique.
got.
Same technique. In fact, that sandwich operator where that similarity transform, I tried to do that in closed form on a computer. So
What program do you use?
the sandwich operator with the projectors,
Like the
and then
programming
I
language.
developed the C5 subgroup chain.
Yeah.
C5B.
Uh,
We could look at it offline. A lot of it is online. So
yeah,
Anyway, the
work
thing that
towards it.
is really remarkable is how these things triple cross. That's the thing that's screwy about this, that you get levels that go cross each other in a triplet. And we had noticed this a long time ago, a triple level crossing point in methane at J equal 10. That's a nice 10 mod 4 is 2 mod 4. This is an A2T2E cluster right there, and then again right there, but this one actually is experimental result. All of them in low J, no tunneling splitting, it's gone. Where'd it go? You know, is this an accident? And then, what's this crazy thing right here? They're all over the place. This is some kind of weird supersymmetry. Wigner would not like this. These things, well, it's hard to say what he would like. You know, I shouldn't speak for him. But what we do is we compare the off-diagonal C2. This is a thing we've already looked at, but this is a type of thing we've already looked at. This is for C2, okay? And it becomes a matrix that the inverse of that matrix has the parameters given in terms of the spectral lines, and this one is the spectral lines in terms of the parameters. So this one really is doing that to see what's going on. So we blow up this diagram right here. We go and look at that thing real close, okay? And boy, there's triple points all over the place. Here's a doublet meaning a triplet meaning a singlet. Bam. Then it happens again, okay? So everywhere you set the parameters 0, 0, 1, if you just have one of these parameters working, you get a triple point. Okay? This represents what the parameters would be to get 0, 0, 0, 1, 0 there. That would be this guy right here. There's a crossing right there that's just a double. But then this dash dash parameter right here, if you go with your parameters, so you have a -1 and a 1 value, okay, well, you're talking about this particular thing here, or right here, or right here. It keeps happening and unhappening. So to me, this is really quite remarkable. So this is a blow-up of the twofold clusters. And, you know, really small scale here, thousands of, a few thousands of whatever our energy units are, and these are arbitrary units, obviously, because this is not something we've had an experiment, except for that methane case that shows this. Okay, so with that, I will end this particular thing. This is an exercise into the unknown for sure, but it's now becoming somewhat known. So we look forward to a future on this. Okay.